So, you turn on the tap, right? And boom, crystal clear water flows out. But have you ever stopped to think about exactly how it got that way? And look, we're not talking about that little carbon pitcher filter sitting in your fridge. We are talking about purifying millions of gallons of water on a massive industrial scale, 24/7. How on earth do engineers and operators tackle a monumental challenge like that to keep the public safe? Well, welcome to The Explainer. I am super excited to dive into this today because we're going to explore the high-stakes, highly technical, and honestly, fascinating world of water filtration. We're going to look at the incredible arsenal of tools that water treatment operators use to strip contaminants out of raw water sources, turning them into that safe, pristine drinking water we rely on every single day. All right, here is our game plan for today. 1. The core of water treatment. 2. Traditional media filtration. 3. The microscopic membrane barrier. 4. Operating the filters. And 5. The backwash process. Let's get right to it. Section 1. The core of water treatment. The critical barrier between raw water and public safety. Now, it's really important to understand that in a conventional treatment plant, filtration isn't just another step. It is the critical, non-negotiable finish line for water safety right before disinfection. Think of a standard surface water plant kind of like a giant assembly line. First, you pull in the raw water. Then you mix in chemicals during coagulation and flocculation to make all those tiny suspended dirt particles clump together into larger, heavy flocks. Next, you let those heavy flocks settle out in a sedimentation basin. But even after all that settling, the water still isn't perfect, and that is exactly where filtration comes in. It's the ultimate physical barrier, the absolute gatekeeper that strains out whatever suspended solids are left, turning cloudy, risky source water into polished, finished water. Moving on to Section 2, Traditional Media Filtration, the gravity-fed workhorses of the treatment plant. Okay, this beautifully illustrates the two extreme ends of traditional sand filtration. On one side, you've got the conventional rapid sand filter. It's essentially sand supported by gravel, and it pushes water through pretty quickly, running at about 2 to 4 gallons per minute for every square foot. But on the totally opposite end of the spectrum, we have the slow sand filter. And when I say slow, I mean massively slower, around 0.05 gallons per minute per square foot. And here's the wild part. Instead of just physically straining the water, a slow sand filter uses a biological layer that grows on the very top, known as the Schmutzdecke. I know, great word, right? This living microbial layer literally eats pathogens alive. Plus, because of how it works, it needs minimal pre-treatment, and you clean it just by physically scraping off that top layer of sand. But what if you want to filter water rapidly without the top layer clogging up instantly? Well, engineers figured out that you can basically stack the deck using specific gravity or density. In a basic rapid sand filter, all the dirt just traps in the top few inches. But in a dual or multimedia filter, we layer completely different materials. We put lightweight, coarse anthracite coal up on top. In the middle goes the denser, finer sand. And right at the bottom, we pack incredibly dense, ultra-fine garnet. Because the largest gaps are at the top and the tiniest are at the bottom, the dirt penetrates deeply into the entire filter bed instead of just blinding the surface. It's a real game changer. This brilliant stacking actually lets plants push flow rates way up to 4 to 6 gallons per minute per square foot. Sometimes, though, the raw water coming in is already pristine. Like, picture water from a highly protected mountain reservoir. Super low turbidity, low color. In those specific scenarios, operators can use something called direct filtration. This means they completely skip that massive time-consuming sedimentation step. They just add a little coagulant, do a quick flocculation, and send the water straight onto the filters. It is a fantastic shortcut. But remember, it literally only works if your raw water is consistently top tier. Also, it's worth noting that not all filters are giant concrete basins open to the sky. Enter pressure filters. These are fully sealed, pressurized vessels, so instead of relying purely on gravity, water is forcefully pumped through them. These are incredibly handy for smaller water systems that simply don't have the space for a massive municipal plant. Plus, they are heavily used for targeting specific nuisance minerals in groundwater, things like iron and manganese, often using specialized media inside. Section 3. The microscopic membrane barrier, scaling down to the micrometer level. All right, let's leave the sand and gravel behind and zoom way, way in. As we climb down the microscopic ladder of membrane filtration, every single step catches progressively tinier threats. First up, microfiltration, sitting at about 0.1 micrometers. That's tight enough to snatch up dangerous parasites like Giardia and Cryptosporidium, plus your standard bacteria. Take a step down to ultrafiltration at 0.01 micrometers, and now you're successfully filtering out tiny viruses. Go even smaller to nanofiltration, and you actually start stripping out hardness and complex organics. Finally, right at the very bottom, you hit reverse osmosis, which removes dissolved salts and pretty much all ions from the water. Reverse osmosis, or RO, is absolutely the ultimate barrier. You see, normally in standard osmosis, water naturally wants to flow from a pure state to a salty state to dilute it. RO fights nature. It literally applies massive pressure to a highly concentrated or salty solution, forcing pure water molecules to squeeze right through a semi-permeable membrane, leaving all those dissolved solids behind. The result? A beautifully demineralized liquid. Section 4. Operating the filters. The tension of keeping the system clean. Designing these filters, that's really only half the battle. Operating them is where the actual tension comes in. Meet your first villain of filter operation, head loss. Basically, as a filter does its job, trapping dirt, clay, and all those microscopic flocks, the tiny spaces between the sand or anthracite grains get clogged up. This creates resistance. The water has a much harder time pushing through, causing a drop in pressure, which we call head loss. As this head loss shoots up, the filter's efficiency totally plummets. But wait, there is a second, honestly much scarier villain, turbidity breakthrough. Actually, let's just call it what it is, a system failure. If an operator ignores that rising head loss and pushes a filter too far past its limit, the pressure literally forces the trapped dirt and solids straight through the entire media bed. Suddenly, dirty particles just burst through into the clean, treated effluent. When breakthrough happens, that filter run is instantly over. Done. The water is no longer safe. So what is the magic number to prevent this? It's 0.3. Specifically, 0.3 NTU. NTU stands for nephelometric turbidity units. It's just how we measure cloudiness in the water. Under the interim enhanced surface water treatment rule, for conventional or direct filtration plants serving over 10,000 people, the combined filter effluent must be 0.3 NTU or less in 95% of their monthly samples. That is a strict, non-negotiable regulatory standard. It guarantees the water is clear enough that pathogens simply cannot hide from that final disinfection step. Which brings us to Section 5, the backwash process, the explosive cleansing sequence. So, how exactly do operators fight back against head loss and breakthrough? They hit reverse. A backwash is exactly what it sounds like. Operators blast clean water upwards through the bottom of the filter at a massive rate, usually 15 to 20 gallons per minute per square foot. This sheer physical force actually lifts and expands that heavy media bed by 30 to 50%. Often they'll even blast compressed air into it in air scour to really scrub the grains together. After 10 to 15 minutes of this violent washing, the dirty water is drained off. But here's the kicker. They don't just send the very next batch of water out to the public. No way. They do a crucial filter-to-waste step, discarding the first few minutes of high turbidity water until the bed perfectly settles back down and the effluent is totally clear again. And let me tell you, if an operator messes up this backwash sequence, things get really gross really fast. You will literally see physical signs of failure. We're talking mudballs forming, actual slimy clumps of dirt and polymer that sink deep into the bed and just ruin the filtration. You'll see deep cracks forming right on the surface of the sand. You might even experience sidewall pulling, which is exactly what it sounds like. The entire media bed shrinks and pulls away from the concrete walls, allowing unfiltered raw water to short-circuit straight down the sides. It's a mess. So the big takeaway here? Maintaining this filtration barrier is not a passive job where you just flip a switch and walk away. It requires constant, relentless vigilance. Operators are continually monitoring head loss, checking effluent turbidity, verifying their flow rates, and crunching precise calculations to initiate backwashes at the exact perfect moment. It is a non-stop, high-stakes battle against physics and microscopic contaminants to keep that barrier fully intact. Which leaves us with a pretty massive question to chew on. Think about it. We've mastered sand, coal, and incredibly tight membranes to catch bacteria and viruses. But as industrial contaminants, things like forever chemicals and microplastics keep growing smaller, more complex, and way more persistent. How are our filtration technologies going to have to evolve to protect our future tap water? It's an engineering frontier that is absolutely vital to our survival. Thank you so much for joining me on this deep dive into the arsenal of water filtration. Keep wondering, keep exploring, and I will catch you on the next explainer.